Okay, we're live. We're live.
Give us a warning next time.
He did. Next time I need to have a little light, up there, live,
It's like
with a
starting
red light.
in 5,
There'll
4,
be
3.
another sign for applause, Or boo,
You do that and you'll have people doing the opposite.
I don't know. I'll have a few bodyguards, like the Jerry Springer show.
Jerry. Or the Steve Wilkos show. Dude, that guy is creepy.
I haven't watched that.
Okay, this guy, I'll tell you later.
Yeah, talk to me later.
Creepy.
Okay, well, let's go ahead and get started. How do you guys like the homework assignment?
That was a piece
It's
of cake
okay.
once I started.
All right, so we have another homework assignment that's kind of like that, except this time we used subtraction instead of addition. Yes?
We're contemplating that all you did was do a find replace all in your text editor to change the file names. Because all you did was change the 4 adds to subs.
Yes.
We thought so.
But unfortunately, you cannot do a global replacement with all your files and expect the answer to work the same way. Yes?
What did you do as far as your grading scale? Because I don't think that would work with your grading script.
My grading script is going to, I would download every single tar.gz file from this class, homework. There's a Dropbox, quote-unquote Dropbox area.
The difference from add to subtract. Because you can't just do a find replace with that, can you?
No. No, so the script itself has to be rewritten because the impossible cases would also change a little bit. So I will have to. All the impossible cases are manually graded for sure because I have to read the explanation of why something is not possible.
So we're all getting Fs for those, right?
Maybe with some people. Yes.
If it's possible, were we still supposed to have put in an explanation field?
If it is possible, you don't have to put in an explanation.
It said that in the instruction.
I didn't read. Who reads instructions? We're all men here.
Remind me not to write recommendation letters for you to get a job in a nuclear plant.
Homework can do it. Come on, then.
Okay, so let's talk about the new homework assignment first. It is almost exactly the same as add flags, except this time we use subtraction. Okay, so we will talk about the context of subtraction and talk about what those flags really mean when you use subtraction instead of add. Okay, you will find that subtraction is actually more useful because you can also use subtraction for comparison. Okay, and a lot of these flags are really useful in the context of comparison. Okay, but understanding addition first, does not hurt because these flags are still affected in about the same way. So this is your new homework assignment. You have, as usual, 1 week to work on it. The only change is here. Instead of add L, we have subtract L, subtract long. But the way it works is basically the same thing. We still have the 16 files that we have to create, and you still have to spot the impossible cases, explain the impossible cases. The impossible cases are not going to be exactly the same. So there are differences between the add and the subtract. So the explanation would not work exactly the same way either. Some of those will be about the same, but some will not be the same. Yep.
Can we have a signed 0 in subtraction yet?
Signed 0.
Yes.
Well, 0 is already signed. It is just non-negative.
Yes, but is there any way we could have that leading bit be 1 and have it still be 0?
No.
Okay.
That
Just
number
making
cannot
absolutely
be,
sure.
It does not represent the 0 that way. There's only one bit pattern for 0, which is all zeros in all bit positions. Okay, so this is your new homework assignment. You have 1 week to do it, and but what will help you in this case is I will talk about the answer to the add flag assignment. So maybe that will help you out in the process, especially when it comes to proving the cases that are not possible, because I think that's more difficult than finding cases where it is possible. So we'll start with that. Let's go ahead and start with a text editor. I'll use that to explain stuff. And save the file in today's folder. I forgot to upload the one from last week or on Tuesday. No one reminded me. Looks like nobody really needs that material. Okay, so let's go ahead and get started with this homework, with the add flag homework assignment. Okay, all flags are turned off. How do we make that happen?
Adding 1, 1.
Okay, adding 1 and 1 will do. Okay, 0 plus 1 will work too. Because if you add 0 and 1, what do you do? What do you get? Is there a carry? No. Is the result 0? Does the sign of the result make sense?
Yes.
Yes.
And what is the other one?
Negative.
Is it
It is. Is it negative? It is not negative. Okay. Well, so that's the easy one.
That was the only one I got.
It's one of the ones that you get. Yes. Okay.
There are literally billions of possible answers for that one.
Oh yeah. It's pretty hard not
Like
to find
32
one.
millions of answers.
What about this one? We only have the carry flag turned on. Is that possible? Okay. Give me one example where the carry flag itself is turned on, but none of the other flags.
You take the bit pattern 1, 1, 0, 0 and add 0, 1, 0.
Okay. You just you can also take F F F F F F F F plus 2. Now plus 1 will not give you the carry because it will not only give you the carry flag, but the Z flag will be on as well because F F F F F F F F plus 1 is 0 with a carry. So it's still a useful pattern, but for later on. For this one, I don't want the Z flag to turn on, and plus 2 will do it. Are there any questions about this one? You know, how to turn on just the carry flag itself without any of the other flags? Any questions why the Z flag is not turned on in this case? No questions? How about the sign flag? The result is 1, so the sign is off. Okay. And how about the overflow? The overflow is easy to explain in this case because the overflow for addition can only be turned on if the signs of the two inputs are the same. If they are different, then we don't care because if you're adding a negative number to a positive number or vice versa, the result can be either positive or negative. So there's no such thing as the sign does not make sense when the two numbers are of different signs. Okay, so that takes care of this one. How about this one? X, Z, X, X. Just the 0 flag is turned on and nothing else. That's an easy one. Exactly. Okay. What about this one? Is it the O flag next or the sign flag? Oh, okay. Okay. How about just the O flag all by itself?
It's not possible.
It is not possible. But why is it not possible?
Because you either get CO or
You have to have an associated C or S with it.
Okay. Well, let's take a look at the O flag definition itself because that by itself will also give you some idea. Okay. The O flag, if you look at the definition, it is okay. If I use X, Y as input and Z as the output, then it is the most significant bits of the input and the most significant bit of the output. It is X, Y, not Z, or not X, not Y, and Z. Okay? X and Y being the most significant bits of the input, and Z being the most significant bit of the output. Okay, so these are the two distinct cases where the O flag can be turned on. Let's look at the first one. Okay, in the first case, X, Y, not Z. If this whole thing is a 1, what is it implying?
that X and Y and then 0.
Implies that X, Y are both 1s. Okay, and what is that telling you? If X, Y's are both 1s and Z is not, that means you must have triggered one other flag.
The carry.
The carry flag must have been triggered, okay? Because 1 plus 1 is 0 with a carry. And that carry has no other place to go except into the carry flag itself, okay? This will trigger C equals 1. So that means, if I turn on the overflow flag using the first part of the equation, the carry flag has to turn on as well. Well, let's take a look at the second one. What if it is the second case, not X, not Y, and Z? Well, that by itself, because Z is 1, but what is Z? Z is the most significant bit of the result, which is also called the sign flag, right? So if the Z flag is on, then the sign flag has to be on too. Okay, so this 1 equals 1 implies that z equals 1. This will trigger the sign flag being 1. So this means, this is a good pattern because every time you see O without either C or, what is the other one? Sign, all of those patterns are not possible and you can use exactly the same explanation. Is that okay? Okay.
Even with subtraction? Use the same explanation with the subtraction. All the ones are...
That's your homework.
Oh, see, I thought you were talking about this.
Good try though. Okay, so that will explain not just XX, OX. It will also explain anything that involves these particular combinations. So that means ZX, OX can use the same explanation. Okay, what about having both C and S being on at the same time? In other words, let me just give you this. What about C, X, or C question mark? Okay, question marks means it can be on, can be off. I don't even care about that for particular. I don't care about the Z flag at this point. So what about having the carry flag on, having the overflow flag on, and also having the sign flag on at the same time? Is that possible? Well, let's see whether that's possible or not. The first case, which is XY not Z, will trigger the carry flag, but it will also at the same time do what? The sign flag is going to be off. Okay?
0 can't be signed.
Okay. XY not Z equals 1 implies two things now. Okay? I should have added this one a little bit earlier. Implies Z equals 1 as discussed earlier. But the sign flag will also be a 0. Now, how do I know the sign flag is a 0? Because not Z is 1. Okay? And Z is the most significant bit of the result. Okay? And what about the other one? The other case is not X, not Y, Z. This one implies the sign flag is a 1. But the carry flag cannot be a 1. How do I know for sure the carry flag cannot be a 1? You have to look at the pattern. 0 plus 0 is a 0. Okay? Now, can I get a carry when I know one of the component is a 0 in the addition? Well, there you have your proof. Okay? But Z has to be a 0 because 0 plus 0 is 0 without carry. Okay? That takes care of the first addition in the column. The second addition is going to be 0 plus something. That could be 1. The question mark can be a 1. It doesn't even matter because 0 plus question mark is question mark without carry or with a carry of 0. So that means the second case of the overflow flag being turned on will guarantee that the carry flag has to turn off when the sign flag is on. Is that making any sense? I'm not even looking at it from the arithmetic perspective. This is all purely from the perspective of the gate logic, what a half adder would do. So that takes care of CXOS and CZOS because they both have all three flags turned on are impossible because of this. Okay, so how many cases have we taken care of at this point? We have 1, 2, 3, 4, 5, 6, 7. Okay. Yep.
Can we go ahead and cross off all the other ZS combinations because we all know
that's
0
that's
can't be
also a
signed?
good one. Okay, C question mark
ZS.
S. Oh, okay, sorry. It's question mark question Z question mark S is impossible. Okay? Well, this one is pretty easy to understand. Okay? Because the Z flag is the negation of the disjunction of all the bits. In other words, it is the negation of, okay, let's see. How should I do it? Okay, Z0 bracket. This is bit 31 of the result, or bit 30 of the result plus blah, 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 and all the way down to bit 0 of the result. And what is the sign flag? The sign flag is 31. It's the most significant bit of the result. So that means if I have the sign flag being a 1, this entire disjunction is guaranteed to be a 1 because it is a big O disjunction of all the bits. If one bit is on, then the whole thing is a 1. But not 1 is a 0. So that means if the sign flag is on, is a 1, we are guaranteed the Z flag has to be a 0. And therefore, they cannot both be 1 at the same time. And that takes care of 4 combinations. Now, one of which is already covered a little bit earlier because there are multiple explanations of why that pattern is not possible. So this will take care of CZ XS. It will take care of XZ XS. It will take care of XZ OS. It will take care of CZ OS. All of these combinations are now taken care of. Okay. Any questions at this point? Yep.
The C question mark OS, is that one of the flags around the homework, and is the question mark supposed to be an X?
No, the question mark means I don't even care what it is. It can be a C here, can be a lowercase x. This can be a uppercase O, can be an X. It's just that these two cannot turn on at the same time, regardless of all the other flags.
So as long as Z and S is on, the other two can't turn on no matter what?
That's correct. That's basically what this is explaining, is Z and S cannot both be 1 at the same time.
That's what the same thing you're saying on the C and the question mark OS. No matter, as long as you have that combination, the next one after C can't be turned on. It won't work for the one on the
This
top
is saying
question
don't
mark.
even look at these two.
Yeah.
If I just focus on Z and S, they cannot both be on at the same time. So that means all 4 combinations like these will be accounted for by this explanation.
And it goes for the same. But what about the one above that?
The one above,
The C and the question mark OS. The one you
this one here, that
Yeah.
means the Z flag is we don't care. It's a don't care.
Yeah.
Yeah.
So no matter what, it just still that combination has to be.
That's why it explains these 2 cases.
Okay.
Okay. Okay, so I'm losing track of which ones are already explained. So I'm going to have to copy and paste from my own notes here, just so that I can keep track of which ones are already done. It's always the tedious stuff that is the most difficult. Okay. All right. So we have taken care of this one. Okay. We have taken care of all the ones where Z and S are both turned on. Okay. So this one is okay or taken care of. I'm just marking which ones are already taken care of. Okay. We have taken care of the ones where only the overflow without the carry or the sign is on. So this one is taken care of. And let's see, O and Z. Okay, that's taken care of. And which one? We have the CXXX, that's taken care of.
All of the individual flags have been taken care of. All, I think you did everything except that one.
The sign is, the sign is easy.
Well, the zero is taken care of by itself.
Oh, Z by itself is taken care of, like that. See, if I were to do this homework assignment, this is the difficult part, is to keep track of which ones are done. But a lot of times it really is, it's all the details. So sometimes you will miss 1 or 2, and then when you turn it in, you lose the points of the ones that you forget to do. Yep.
If you look at your directory listings, all the ones with .o files have been done.
But someone can miss a .o file, just forget the whole case altogether. Okay, let's take care of XXXS. This is also an easy one. How do we make this happen?
0.
-1 plus 0. Okay? So that's not too difficult. So that's taken care of. The sign and the overflow. Well, if you want to turn on these two, what you need to do is to go back to the equation, okay, the overflow flag equation, which is right here. Okay? And we want the sign flag to be on. In other words, we want this component to be a 1. Does that make sense? Because I want overflow to be a 1, I also want the sign flag to be a 1. This combination, this conjunction is the only case where you can have the sign flag also turning on. Because the other one explicitly says, we want the most significant bit of the output or the result to be a 0. So that means you have to focus on this case. The two numbers have to be non-negative. The result has to be negative. Okay, so let's take care of that. So that would be XXOS. One easy way to get this to happen is to say
4, 0.
4, 1, 2, 3, 4, buzz, like that. Because the result of this is 0x800000000. Okay? And that makes it happen. Because 1, there's no carry. It's perfectly fine because it does not. This is the second most significant bit. This is the second most significant bit. And it does not generate a carry for the entire operation. The Z flag is also turned off because it is non-zero. But at the same time, the overflow flag is on because this is bit 30. This is bit 30. In other words, this is non-negative, this is non-negative. But this is bit 31, which means the result is negative. I'm adding two non-negative numbers and somehow end up with a negative number. So the sign does not make any sense, but you can also look at this from the perspective of bitwise operations. It explains the same thing exactly the same way. Question? Okay, so that takes care of this guy. And now we are down to this one. Having the carry and the sign flag being on at the same time. Without the overflow and also without, whoops, did I move to the wrong place? Carry and the sign at the same time. Okay, C, X, X, X. But first of all, is it possible? It is possible. And how do we make that happen?
C0000000 plus C0000000.
What about this? That'll do it.
I don't know.
Okay, well, let's take a look. I know this is the correct result. This is FFFF, which means all the bits positions are 1. So is the second operand. When you add these two, it will come up with this answer, which is non-zero. Okay, that's good because the Z flag is a 0 in this case. It's supposed to be a 0. The sign flag is on because the most significant nibble being an F means that the sign flag is on. The most significant bit is on. So that explains that. The carry flag is on because we are adding the MSB of this one. The most significant bit is on with this guy, and so is this one. And that 1 plus 1 triggers a carry automatically. So we know the carry flag is going to be on. The overflow flag is off because this is a negative number plus a negative number ending up with a negative number. The sign makes sense. Okay? So that's why this pattern can be generated using this particular pattern. Yep.
Is there a way to think of negative decimal? I mean, negative number convert to the binary code?
Yes, you can. If you know how to represent a number in 32-bit, this is the same thing as saying -1 plus -1 equals -2. Because this is the bit pattern to represent -1 as a 32-bit number. And this one here is the bit pattern for -2.
What about like negative 100 or something like that? Is there a method to calculate what is the?
Yes. Okay. That's a good question. The question is it's a little bit digression from what we are talking about, but I think it's a good question. The question is, if I want to represent in decimal minus -100, how do I find the bit pattern? Is that the question? Okay. So I would do it this way. First of all, you find the bit pattern for, let's say, 100. Okay, so 100 is what? 64 plus 32 plus 4, right? Okay, so that makes it a fairly easy, binary number to represent. So that would be, let's see, 1 1 0 1 0 0. Is that right?
Yeah.
Okay. And then you just have to add a whole bunch of zeros in front of it. Okay. That's a 16-bit number. Okay. That's how you represent 100 in base 2. Okay? Is that making any sense so far? This is just a way, I cannot do subscript 2, and that's why I'm just using a 2 after the parentheses to indicate this is a binary pattern, as opposed to this one, which is a base 10 number. Once I have this, how do I find the negation of that? Yep.
I think it should be 0, 1, 1, 0, 0, 1, 0, 0, 0.
One in the 60s. Or the 60s.
This is 8.
What did I miss?
0, 1, 1,
Okay,
0,
this is
0,
0, 1,
Far right.
0, 0, 1, 0, 0,
1, 2, 4, 8.
0 right there. Yeah.
Oh, that's okay.
This is 60.
Do a shift like that. Okay, thank you. Okay. But the bottom line is, this part is easy because you can do the translation using a calculator. Okay, just punch in 100 and find out what is the bit pattern. Once you have the bit pattern, finding its negation is going to be just finding the 2's complement of this thing. Remember 2's complement that we talked about? I claimed that it is the same as negation in arithmetic. So what you do is you apply the 2's complement to this entire pattern here, which is finding the 1's complement of this pattern plus 1. And that means you flip all the zeros into 1's. And then add 1 to it. And that becomes, okay, I have to put all the equals here. And that becomes basically the same thing up to this point. And then you have 1, 0, 0 after that. So the binary representation of 100 in decimal is going to be this particular bit pattern. Now, obviously, you don't want to type that in, because it's a lot of zeros and ones, and if you miss one, it's not going to work. So the way to do this, if you want to put it into your program, you want to do it in hexadecimal. And this becomes, F, 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 F. This is 9, and that's C. But after a while, if you program in assembly, a lot, you can map, the hexadecimal numbers to the binary patterns just like that, because there are only 16 entries. Yep.
How do you figure out whether it's an F or a 9 or a C? Like, what told you? Because I see for all the ones that
because of the lookup table that we talked about 2 classes ago, you have the hexadecimal digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F.
Oh, yeah,
to represent 0, 0, 0, 0 all the way down to 1, 1, 1, 1. So that's why I group all the binary digits into groups of 4, because every group of 4 binary digits is 1 hexadecimal digit. And that's why I can do the translation. These 4 goes to F, these 4 goes to the next F, and so on.
So to figure that out, we have to go through all those steps right there to get that, and we can use that as an explanation as to why it will work or not.
No, this one has nothing to do with the homework assignment. It is just to answer his question about how do I find the binary representation of negative 100 in decimal.
So we use the binary representation for your explanation though up there, right? For the homework, the zeros. And
For the homework, for impossible cases, you have to explain it. For possible cases, you don't have to explain it.
So for the impossible cases, you can use the binary representation as an explanation. For possible cases, or no? I'm just wondering why you used it, and if I'm supposed to use it too, basically, for explanation, because you put it up there.
You mean here?
Yeah, at the very top for the answers for the homework. Yeah, those ones below it, where you did the zeros. Yeah, those ones right there.
This one?
Below it, the ones
This
with
one?
the zeros and X's and F's. Yeah, that one. Is that an explanation for why you?
No, this one does not require an explanation because there is a case to make it happen. So there's no explanation needed.
So what was the point in writing it in binary representation? Like
To answer his question.
No, for the homework one.
For the homework?
Yeah, isn't that part of the homework problem right there? The CXXS.
CXXS is a flag pattern that you have to make it happen or explain it is not possible. I just find an example to make it happen, so I don't have to explain anything.
Example. Also, that's the example of.
Yeah, you just replace the question mark from the first question mark with -1. You replace the second question mark with another -1, and the bit pattern or the flag pattern will happen.
But you can write it either way. You can write it in -1 plus -1 equals
Yes.
-2 or 0. Okay.
Yes. Okay, so that takes care of this one. Okay, here's the next one. Can I make the carry flag turn on and the overflow flag to turn on?
Yes.
Okay. But not the sign. Okay. So we have C, X, O, X. Okay. Now, if you look at this pattern here, it will tell you where to look because the sign flag is off. Okay. If the sign flag is off, you have to go back to the definition of the overflow flag. If the sign flag is off, it matches the first case. So that means the most significant bit of the two numbers as input, they all have to be turned on. In other words, you're looking at two negative numbers, adding two negative numbers to have a positive number. Okay? Or non-negative number as the result. So where are we? Oh, I lost. Oh, right here. Okay, right there. Okay, so you start with two negative numbers and you want to end up with a non-zero number in the end, and yet the overflow flag will still be triggered. So one way to do it is to say 800000000 plus 0x800000001, because that will give you this as an answer. Now, but giving you this answer will also tell you that the overflow flag has to be on, because this 8 here means the MSB is on, the most significant bit is on. This is also having the most significant bit on. This one is having the most significant bit off. So you are having two negative numbers and the sum is non-negative. And therefore the overflow flag is on. The carry flag is on because MSB is being 1, MSB being 1 automatically triggers the carry flag. The Z flag is off because the result is non-zero, and the sign flag is off because the result does not have the most significant bit turned on. We also proved that it is not possible to have both the sign and the carry flag being on at the same time when the overflow flag is on. So that's pretty much done already. Okay. So let's look at our table and find out which are the ones.
You say that it's not possible to have the sign and what are the flag? The carry flag?
The sign and the carry flag and the overflow cannot all be on. Those three are exclusive. So this one is already explained. Just did it. Okay, this one is having the carry and the Z flags turning on, but without triggering the sign or the overflow flag. Is that possible? Well, you have to be a little bit careful about this one, because if you're not careful, you can accidentally trigger the overflow flag. So we have C, Z, X, X here. You have that's it. Okay. The reason why this happens is because when you add 1 to all ones as a binary pattern, the carry will get rippled. It will just get propagated through the entire calculation, and it will end up with one single carry as the last result. So that's why the carry flag is a 1. But the result is a 0, and that's why the Z flag is also turned on. The overflow flag is not on because the two inputs have different signs, and therefore there's no question. You don't even have to ask why it is off, because when the inputs do not have the same sign, you're guaranteed not to have the overflow flag turn on. And the last one is the sign flag, and you can see the result is just 0, which does not have the most significant bit turned on. And we're down to the last case, which is CZOX. Okay, is that possible?
Yeah.
Okay, that's CZOX. The way to do it is something that seems like something that we have done already, but this time it is, both are exactly the same, and it ends up with this pattern here. this 8 and this 8, they're both the most significant bits, so that triggers the carry flag to turn on. The result is 0, and that's why the Z flag is on. The overflow flag is on because this is negative, and this is non-negative, and as a result, the overflow flag is also turned on. Okay, and that takes care of all the cases. Any questions about this? Yep.
I got a question. I know if you write 0x, you're switching to base 16. Is there a way to write base 2?
Say that again?
Is there a way to write base 2?
I think it is 0t.
0
you know, is it 0b? Okay, 0b is a prefix, and you have a whole bunch of zeros and ones. Yep.
32, otherwise the compiler.
Yeah, it is. But it is quite painful to have to specify, 32 zeros and ones.
Copy and paste.
Yeah, but copy and paste is still painful.
Because that means
It's
you
still
write it
more
at one
painful
time.
than copy and pasting 8 hexadecimal digits. Yes.
Are you going to have problems with our assignments if we used a modified GDB init different from what you provided?
As long as when I run your program, it still behaves the same way, it should be fine.
The program to the GDB init, or will you just overwrite those?
I'll just go ahead and overwrite it.
Okay.
Oh, because you changed the output to match the file?
Yeah, because you had the
That
bits
makes sense.
in the wrong order. And I
Yeah,
added my
I
B
know.
checkpoint R I R E A X flags Q to the end of it.
Yeah, I know. Okay, that's fine. All right. So, are there any questions about the add flags assignment? No questions? Okay. If there are no questions, we're going to move on and start to talk about subtraction and how the flags are set in the case of a subtraction.
That was subtraction you had open.
Hmm?
You had subtraction open.
Yeah, but I want to talk about the subtraction slide.
Ooh, can you click on that one that was grayed out just below what you clicked on?
Hmm?
Could you click on the one that was grayed out just below what you clicked on?
Okay, so last time we already talked about subtraction, and here we've gone through all this stuff here. I know we have gone through the multi-bit thing, the half subtractors, and basically they're the same concept as a full subtractor. Basically, if I look at it this way, it's the same way as full adders, except they're subtractors. Okay, so we still have to stack them up the same way. There's a picture somewhere. So this picture also applies to subtractors, except you have half subtractors. Adding 2 of the half subtractors will give you 1 full subtractor. And that's basically that concept. The borrow from the most significant bit. Okay? So that means, okay, let me just give you one example to show you what I mean by that. The example is going to be in the text file, so this way we don't lose it. Okay. The easiest example I can give you is something like this. What is 0000 minus 0001 in binary? Okay. Well, you already know the result is -1, but we cannot represent -1. There's no way for the sign to be independent. So let's see how we can actually carry out this subtraction here. This is the subtraction for the borrow flag, and this is the final answer here. Okay. 0 minus 1 is 1 with a borrow. 1 minus 0 is a 1. 0 minus 0 is 0. 0 minus 1 is a 1 with a borrow. 0 minus 0 is 0. 0 minus 1 is 1 with a borrow. 0 minus 0 is 0. 0 minus 1 is 1 with a borrow. This is the borrow flag. Yep.
I have a quick question. So you only borrow when the end result is a 1, basically, because I'm not sure how you borrow when you're subtracting.
We talked about that last time.
Yeah.
It is because of the way it works. Okay, the borrow flag is defined to be like this one here. if the first bit, let's go back even one more slide. That's it. Okay. 1 minus 0 is 1 with a borrow of 1.
0 minus 1.
0 minus 1 is 1 with a borrow of 1. Sorry. That's it. We talked about that last time.
0 minus 1.
Yep. And I think it is important to clear the concepts, up, at the end of a class before we start up the next class. So that means, you have to study a little bit after the class, just to make sure that everything that we talked about in that class is good. And then, that just makes it more effective, for the following class. And I forgot where I was. Okay, we talked about this one, and this is the example. This is the borrow from the most significant bit. And in terms of hardware, it is the same as the carry flag. In other words, there's only one bit to represent the carry from an addition and also a borrow from a subtraction. And that you have to be careful, because if you rely on the fact that a carry flag will be remembered, and you carry out another subtraction after the addition, then your program won't work correctly, because the carry flag will be overwritten by the subtraction instruction, because the borrow flag is the same physically as the carry flag. Yep.
Does GDB know the difference, and if so, how?
No, GDB does not know the difference at all. It only reported as the carry flag, which is the more common way to refer to that flag. We never refer to it as a borrow flag most of the time. Yep.
When we are doing subtraction or addition operations in rapid succession and need to evaluate the results of them later based on the results of those flags, is it acceptable practice or common practice to copy the flags to another register like RAX or R1 or R8?
The most common, okay, that's a good question. The question is, this is a little bit, looking ahead of time, but the question is, what if we have to carry out a comparison, which is basically a subtraction, but we cannot utilize the result of the subtraction just yet, and then we have to perform an addition that will basically overwrite all the flags. So the question is, how do we deal with that case? And Christ was saying, should we copy the flag register to somewhere so that we can use it later on? And the answer is, there's a better way to do it. You can use push and pop. Okay, you can save the status register and then pop it back when you need it. So that way you can still use the conditional branches easily without blowing a register on the side. Okay, so we'll talk about push and pop later on. But remind me to talk about that particular application of push and pop, because it's a useful way to use push and pop. But for the time being, we don't have to worry too much about it at this point. Okay. So now we are done with binary subtraction, and we are moving on to subtraction and comparison, which is a really easy slide. The subtraction instruction of the i386 is much like the add instruction. In other words, if you know how to use the add instruction, and by now you should, you already know how to use the subtraction instruction. The only difference is the subtraction instruction is a little bit counterintuitive, because if you look at this instruction here, the first operand is subtracted from the second operand, and the result is stored in the second operand. In other words, we still keep the same terminology. The first operand in this case is an immediate operand with a value of 32. It is still called the source operand. The second operand, EAX, is still called the destination operand. But the subtraction is EAX minus 32, and the result is stored into EAX. Yep.
So it's basically the same as in C, writing EAX equals EAX minus 32?
Correct. It is the same as saying EAX minus equal 32. Yes. It's better to use the minus equal, because that really emphasized that one operand that supplies a value to be subtracting will also store the result of the subtraction. Are there any questions? Let me just copy that because I know that when I say something, it's a little bit harder to remember what I said. So the answer is this is the same as quote unquote EAX minus equal 32. in C.
You forgot a semicolon.
Well, that's why this is pseudo C. How's that? Pseudo
If
C.
it's in a comment, it doesn't need the semicolon.
Hmm?
It's in a comment, it doesn't need its semicolon.
Oh, you got me.
Where's the pound sign?
Right after.
Okay, so do we have any questions about the subtraction instruction? All the same rules apply. Okay, in this case, only the first operand as the source operand can be an immediate operand, and you are still constrained by only having up to one memory operand. Okay, so the same constraints apply to the move instruction, the add instruction, as well as the subtraction instruction. Okay, the only difference is what they do, but in terms of the operands and also restrictions on the operand, they are also exactly the same. Okay. And the next instruction is CMP for compare, and the compare is exactly the same as a subtraction with only one minor difference. It does not store the result. That's it. Okay, but hold on a second here. If it does not store the result, how do we use the result of a compare? I mean, compare is meaningless unless we can utilize the result of compare. Now, this is a big deviation from what you understand in the C class, because what you do in a C class? In a C class, switch back to my notepad here. In a C class, you typically would say if x is less than y, do something here. Okay. Blah blah blah. Just so that people cannot complain.
What are the types of x and y?
Okay, but in assembly programming, it's not quite the same way because there's no such thing as compare and check less than. It is not one single instruction. They are two different instructions. In other words, this is going to be done in assembly by saying CMP yx, and then you say if less than jump somewhere. Okay, it's a little bit too early to talk about the second part, and that's why I just kind of verbally describe what it is, but it's basically implemented by two instructions instead of one. Okay, and that is kind of interesting because how can the second instruction know that y is less than x or x is less than y?
L flag.
The L flag. Exactly. So the flags are very important in comparison because that's how your program can decide, oh, should I jump or not? How do I check for equality? How do I check for less than? How do I check for less than or equal to? And so on and so forth. The compare instruction itself is a subtraction instruction, which is basically sign insensitive. Okay, it works on signed numbers, it works on unsigned numbers just the same. It is the flags that are sign sensitive. Okay, so that's a good introduction or a good lead in to the next topic. Whenever it comes up. Okay, so the next topic talks about the same flags that we have talked about so far, the carry flag, the zero flag, the sign flag, and the overflow flag, but in the context of comparison. Okay, remember comparison and subtraction are exactly the same thing, except one stores the result and the other one does not store the result. So I would just combine those two instructions into the same discussion because they typically are the same in terms of how they change the flags. Okay, you look at the carry flag here, it is nothing more than the borrow from the most significant bit. Okay, or borrow from the bit that does not exist, that is one beyond what you can store. Okay? And the next one is the zero flag, and guess what? It does not change. The definition stays exactly the same. You're taking a disjunction of all the bits of the result of a subtraction and you negate it, which means it is exactly the same meaning as in addition. That part does not change. The sign flag does not change either. It is just the most significant bit of the result. That part does not change. The overflow flag does change. This is the one that is changed. Let's not look at this equation here. Let me just give you a few examples so that we can understand why the logic or the bitwise operation looks like this. So let's go to my editor, and I'll show you a few examples. We'll start with the one that we have seen already. Let's start with this one. Does the sign of the result make any sense?
Yeah.
Well, okay, let's name what is, well, let's name the signs, okay? We are subtracting a non-negative number from a non-negative number and end up with a negative number. Can that happen?
Yes.
So the sign makes sense,
Sure.
okay? Now when does it not make any sense?
Take a negative and then back to positive.
Okay, we can try that. So we want to take a negative number minus a positive number and somehow end up with a positive number. Okay, when I say positive, it really means non-negative. Okay, because 0 is also non-negative. 0 is not negative. Okay, let's see if we can make this happen. We can take 1000 as a 4-bit pattern, minus 1 from it. Okay, pretty easy subtraction. I'm still going to carry out the entire calculation, just so that we have more practice to do it.
Yeah, let's totally get an underflow.
Okay, so 0 minus 1 is 1 with a borrow. 0 minus 1 is 1. 0 minus 0 is 0 with no borrow. 0 minus 1 is 1 with a borrow. 0 minus 0 is a 0. 0 minus 1 is 1 with a borrow. 1 minus 0 is a 1. 1 minus 1 is a 0. And there's no borrow from the digit that does not exist in the outside of what we can store. Okay? So in this case, if I want to spell out all the flags, it's not too hard. The carry flag, which is the same as the borrow flag, is going to be a 0. There's no borrow in the calculation. The Z flag is going to be a 0 because the number is non-zero. And I will skip the overflow flag. I will go to the sign flag first. The sign flag is a 0 because the most significant bit is a 0. But the question is, what about the overflow flag? The overflow flag in this case is a 1 because the first number is negative. The second number is non-negative. I am subtracting a non-negative value from a negative number and somehow end up with a non-negative answer. That does not make sense. Okay? So that's one way to get the overflow flag to turn on in a subtraction. Yep.
So you got to go with that calculation first and not by the 0 that you get at the end. You have to go at the top and do a calculation. Basically, you have to subtract the last 2 digits, which is 1 minus 0, and just go by the 0 flag from there.
I don't think I understand the question.
Like, so you see where the cursor is right now and it says 0? You see where the cursor is right now on the 0? Wouldn't that usually be the overflow flag?
No.
Is 0? That wouldn't be?
No. The overflow flag, if you look at it from the arithmetic perspective, the overflow flag means the sign of the result does not make sense. It is not a sign. It is saying the sign does not make sense. Okay, so you cannot just look at one bit and determine whether the overflow flag should be on or off. Okay, so let's look at the other case. What about I take a positive number or non-negative number to begin with, subtract a negative value from that, and okay, I should change this notation here, negative minus positive, right? And in this case, if I end up with a negative value, the sign makes no sense because I should end up with a positive value when I subtract a negative value from a positive number. Well, let's make that happen. Now you can probably you probably can already guess how I work with these numbers. I look at the most positive number that they can represent, and then I work from there. Okay, that's how I can generate all these cases. They're all borderline cases. They're all at the boundary already. So the most positive number I can represent using 4 bits is 0, 1, 1, 1, because that's the largest number with the most significant bit turned off, and that makes it the most positive value that can be represented using 4 bits. And I can just subtract just about anything from it, including 1, 1, 1, 1, which represents -1. So I look at this and have another row for just the borrow and look at the result. Okay, 1 minus 1 is 0 with no borrow. 0 minus 0 is 0 with no borrow. I would just put a 0 here. I could have just left it blank, but putting a 0 here is more consistent. 1 minus 1 is a 0. 0 minus 0 is a 0, and neither subtraction generated any borrow. 1 minus 1 is a 0. 0 minus 0 is a 0, and neither generated a borrow. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. So if I look at this calculation, the carry flag, which is the same as the borrow flag, is going to be a 1 because there is a borrow after the entire calculation. If I look at the Z flag, it is going to be 0 because the result is non-zero. If I look at the sign flag, it is a 1. If I look at the overflow flag, what is it? It is also a 1. Why is it a 1?
Because you overflew.
Because the sign does not make sense. I started off with a non-negative number. I subtract a negative value from it, and I end up with a negative number. If you translate the signed meaning of these bit patterns, we are saying 7 minus -1 equals -8. That's basically what this is saying. Yep.
Is there a good way for my bank to do that?
For a bank? I'm pretty sure Obama is doing research on that topic. As will the next president, regardless of the party.
Get our national debt so low that it overflows and becomes positive.
You mean underflow?
Yay,
we'll have a U flag for underflow, right?
Well, that's what you did here, or what you did in the first one. You took a negative number and subtracted from it till it turned positive.
Ooh, that's a nifty trick, huh? Okay.
That's how math works. You didn't know that? That's why we can never reach infinity.
Nah, there won't be any infinity because next year is 2012.
We've got most of the year to keep working.
Just because the tablet is not big enough, now it will be the end of all humanity.
What happened in 2012?
It's the Mayan calendar. They put it onto a tablet, so I guess they ran out of the room. So the calendar ended in the year that we call 2012. So some people take it as that means there won't be any time after 2012, and that's why the Mayans just did not bother to do any type of calendar after that year. Yep.
I heard that the Mayans had miscounted, and that the time that the calendar is supposed, or that we had miscounted from where the Mayans actually started, and that the year that the Mayan calendar was actually supposed to run out was year 2038, and that the date was supposed to coincide with the Unix Y2K38 bug.
I don't care. It's still finite. From a theoretical perspective, it's still finite. Yep.
So whenever we subtract from the negative and positive number, it will turn on the overflow flag, right?
Well, let's take a look at this equation here. That will answer your question. Okay. So in this equation here, it is based on subtracting y from x. So it's basically saying x minus y, x being a n-bit number and y being an n-bit number. And d is the difference, which is the result of the subtraction. As you can see, the equation does not care about anything except the most significant bits of the inputs, x and y, and also the output, which is d. Are we okay so far with the notation? What is x, what is y, and what is d? Okay. And the overflow flag is defined in bitwise operation to be a disjunction. In other words, we have two distinct cases where the overflow flag will be a 1. The first case is, okay, what does that mean? The first number, the one, x is negative in this case because the most significant bit is a 1. Y bar, or y subscript n minus 1 bar, means the most significant bit of y is a 0. In other words, we are subtracting a non-negative number from a negative number. Okay? But what about the result? The result is non-negative. Okay? Because the most significant bit of the result is a 0. Does that make any sense? It does not make sense, right? The sign of the result does not make sense. I start off with a negative number, I subtract a positive number from it, and I somehow end up with a non-negative number. And that's why the overflow flag will be a 1 when this pattern happens. Is that making any sense? Is that okay?
The concept's clear, but the explanation is as muddy as a lake.
Well, Lake Tahoe is pretty clear.
Okay, your explanation is as clear as a puddle of mud, but the concept is clear.
You can use the example of Clear Lake. Because Clear Lake is anything but clear. That's right. It's interesting how they name these, lakes. I guess it's wishful thinking. Clear Lake. Oh yeah, Greenland is a good one too. I like that. They could use a lot of paint.
What about that Newfoundland up in
or
Canada?
do the trick, in the Wizard of Oz. Make everybody wear glasses. Now everything is green again. We should tell our president.
How to make more green?
Yeah, we'll just all wear glasses. All right. So the next one is the opposite. Okay, the first number is non-negative because the most significant bit is a 0. The second number is a negative number. So we are subtracting a negative value from a non-negative value. And somehow the result is negative. Okay? Positive minus negative is negative. Does not make sense. So these are the two distinct cases, but instead of encoding everything in arithmetic meanings, I put everything into bitwise operations. Are we doing okay so far? In terms of concepts, I know the bitwise operations can be a little bit tricky, but in terms of concepts, do we understand why sometimes the sign of the result does not make sense? Okay, very good. So you might think that this is the end of this discussion here because we have already talked about C, Z, S, O, all the flags that we have used already. The big question now is, how do I know a number is larger than another number in a comparison? That's the question. In other words, how do we look at the flags so that we can say, oh, the first number is larger than the second number, or the second number is larger than the first number? Does everybody understand my question?
Yeah.
Okay? Okay. So that becomes the nasty part of the interpretation of the flags. The Z flag is easy. The Z flag is easy because when the Z flag is a 1 after a subtraction or a compare, it can only happen when X and Y are the same. Okay? So that's easy. We understand how to interpret the Z flag. If the Z flag is a 1, that means the comparison, we're comparing two numbers that are exactly the same. If the Z flag is 1, that means the two numbers that we just compared are different. We don't know which one is larger, we just know that they are not the same. Excuse me, I take it back, the other way around. If the Z flag is a 1, that means the numbers are the same. If the Z flag is a 0, that means the numbers are different.
I'm confused what you
I said
I was
exactly.
keeping writing and pretending.
Well, I can also just read my own notes. I can cheat, I guess. Okay? The only time a difference is 0, which means Z equals 1, is when two operands are the same. Which is also saying, Z equals 1 if and only if X and Y are the same. Not if, not only if, but if and only if. Does everybody understand the differences between if, only if, and only if? Yep.
No.
When you say two operands, you mean the two question marks if those two numbers are the same?
The two operands, the two things to the right hand side of the instruction.
And the code?
In the code, in the instruction, yes.
Okay, all right.
Okay, so sometimes in certain architectures, including the Intel architecture, you can also refer to the Z flag as quote-unquote the E flag for being equal. Okay, so there are synonyms to these instructions that we'll talk about later. Are there any questions about the Z flag, or how do we interpret the Z flag after a compare instruction? Okay, it only confirms equal versus not equal. Cannot do anything else. Let's look at the C flag. Now you can see the slide for the C flag is a little bit longer than the Z flag. Okay, so let's find out what it does. The C flag, which means borrow, remember the C and B are exactly the same thing physically. It is somewhat simple to understand, but at the same time, it's also not so simple to understand. So we'll have this pseudo operation here. We are comparing x, y. In other words, we are subtracting x from y. This is the one part that is counterintuitive. We subtract the first operand from the second. The flags are set according to the result of y minus x. What does it mean when c equals 1? That's the question. But let's go set up a few examples and you guys tell me what it means. Okay, one easy example is one that I have already talked about. And this time I'm going to skip the entire calculation. I will give you the end result right away. So in this case, it will give you a borrow at the very end, and the result is 1, 1, 1, 1. Okay. So now the big question is, what does it mean? Okay, and remember which one is x and which one is y. This is our x and this is our y. Okay.
It should be the other way. It should be y and then x.
Oh, that's right. We are subtracting x from y. Well, that depends on which part of the notes we are talking about, so let's be consistent with this part. Sorry. Okay, there we go. Okay. Because I changed the order of x and y, in different parts of the notes. Sometimes I say it's x minus y, but in this case it's y minus x. Okay, but in terms of the relationship of x and y, which one is larger?
X is bigger.
Well, this one is easy, right?
Y is larger.
Y is
Y
is the one that's smaller, right? So in this case, y being less than x, triggers c being 1. Is that making any sense so far? Yep.
How do we know that y is smaller than x?
Because y as a 4-bit number is decimal 0, and x being as a 4-bit number is 1 being a decimal number. Okay, so 0 being y is less than 1 being x. Okay, is that okay so far? Well, let's take a look at the next example, okay, which is kind of interesting. The next one, let's try this one. Okay, we have 0, 0, 0, 0. I'm trying to organize the order of these things. So let's try this one. 1, 1, 1, 1 minus 0, 0, 0, 1. Okay, which is a really simple subtraction. There's no borrow at the end, and the result is 1, 1, 1, 0. Okay? Does that make any sense? I'm skipping all the stuff in between because that would just be taking too long. Okay. But this time, which one is larger? Let me just label the numbers again. This is y, this is x. This is a trick question. Remember the number wheel that we talked about? Remember on one half of the wheel, okay, the non-negative side, those are definite, okay? We don't have any questions. They don't have two identities. But the ones on the other side, remember, they can have a positive representation, or they can represent positive numbers if the number is unsigned, or they can represent negative numbers if the numbers are signed. So this one is special because we have to take the sign portion into consideration. Now, if you look at the first example, okay, let me just make this a little bit more consistent with the other one. Okay, 0 is 0 whether it's signed or not. 1 is 1 whether it is signed or not. In other words, these two particular 4-bit numbers can only be interpreted as 0 and 1 whether it is signed or not. Is that making any sense? But in the second example, it's not quite the same thing because 1, 1, 1, 1 is negative 1 signed. It can also be interpreted as 15 unsigned as a 4-bit pattern. So now things are starting to get a little bit mucky because the result of these two will be different. Well, but tech they are the same bit pattern. Well, that's fine, because this is actually -2 signed, and this is 14 signed. In other words, if you look at the bit pattern of the result, unsigned.
Yeah.
If you look at the bit pattern of the result, if you keep interpreting everything as signed, it still makes sense. If you keep looking at everything as unsigned, they still make sense. I mean, -1 minus 1 is -2. The math works out. 15 minus 1 is 14. The math works out too. But the big question is, can we look at the flag and see which one is smaller and which one is bigger? Well, that's a little bit different, because in this case, if you look at it from the signed perspective, which one is bigger? Y is smaller than X. And yet, C is clear. If you look at it from the unsigned perspective, Y is larger than X, and obviously the C is also clear because we only have one carry flag. It is not, the operation itself, this part here, does not pay any attention to whether the number is supposed to be looked at as signed or not. Is that working out so far? Okay. So that means you have to be careful when you want to see if a number is larger than the other one, because in some cases you can use one single flag to give you the answer. In other cases, you cannot. Okay, of the 4 flags that we have seen so far, in some cases, one single flag cannot tell you the answer of which one is larger. Okay. Let's take a look at yet another case. Okay, let's just flip the operand to see what happens. In other words, let's do 0001. And that's my Y, which represents 1 signed, which also represents 1 unsigned. And we are just flipping the operands, so the number to subtract from 0001 is 1111 as a bit pattern. In the signed representation, it means -1. In the unsigned representation, it means 15. Right? So let's take a look at the result here. The result is, let's see, that will be 2 with a borrow. So there will be a borrow here, and the result is 0010. Okay. Okay. Well, we can always double check, 1 minus 1 is a 0, 0 minus 1 is a 1, 1 minus 0 is a 1, and the other ones work out too. So I'm pretty sure the math works out. Okay, does it make sense? Well, let's take a look here. This is 2 in signed representation, and this is also 2 in unsigned representation. Oh, Tack, something is wrong here. Right? Something is not right. I mean, the signed representation works out. Okay, the signed interpretation, I should say, works out because 1 minus -1 is 2 is right. Okay, nothing wrong with that. But the unsigned interpretation is kind of wonky. Okay, 1 minus 15 is 2. Well, it's not exactly 2. It's actually 2 with a borrow. Okay, what does the borrow mean in the unsigned interpretation?
That the number was too large to
Okay.
15 is bigger.
It means 15 is bigger. Okay, it means the first number is smaller than the second number. In other words, if you want to look at things or if you want to interpret the bit patterns as unsigned numbers, the carry flag, which is the same as the borrow flag, is already sufficient to tell you to confirm the second number is larger or not. Okay? So just to finish up this discussion here, in the signed interpretation, we have Y being less than X, but this time the carry flag is a 0. And if you look at the unsigned,
flag's a 1.
oh yes, thank you. Using the unsigned interpretation, Y is actually greater than X, and yet C equals to 1. Now, if you look at y is rare. Okay, x is greater than, x is less than, C flag is a 1. Okay, so that's fine, I think.
X is greater than Y in the unsigned case.
In the unsigned interpretation, x is greater. Well, that means the other one is wrong too. Okay, there we go. Okay.
The alligator eats the bigger number.
Yes. That's a good way to look at it. Okay, so, but now we can see a pattern, okay? We can see a pattern that when you look at things from an unsigned perspective, whenever y is less than x, the carry flag is a 1. But we don't have such luck with the signed interpretation. Okay, let's go back and take a look at the example earlier here. Okay. So, oh wait. Well, we only have one example to illustrate. But
You
we
can
have-
make more.
We have another one here. Okay, let's take a look at this one. I'm just retrofitting this one for the discussion. Using the signed interpretation, what is that?
7.
That's 7. Using the signed interpretation, what is it?
1. Negative 1.
1. Using this unsigned interpretation, what is that? 7 again. And using the unsigned interpretation, what is that?
15.
It's 15. And what is the signed interpretation of this? That's negative 8. And using the unsigned interpretation, this is 8. Now this is tricky because it's one is the negation and the other one is the non-negative version of 8. Okay. Are there any questions at this point? Let me just kind of pause here a little bit and see if there are any questions. Yep.
On the other one, before this one, how come you did normal arithmetic for 15 minus 1, but then 1 minus 15 equals 2 again and not negative 14?
Because the bit pattern tells me it is 2. I'm just looking at the bit pattern.
So
Okay.
you don't do normal arithmetic?
Hmm?
Look at the bit pattern first instead of doing normal arithmetic for that one?
Yes, I'm just looking at the result of the operation and only interpret the bit pattern. Yep.
I guess the way to look at that is pretty much borrowing 16 and then adding it to 1 and then subtracting the 15 because they're actually borrowing 1 from the next.
Correct. If you look at the borrow, then it makes sense because you're borrowing a 16 already. Yep.
Excuse me, 7 minus negative 1, so it's going to be positive 8.
Sorry? 7?
7 minus negative 1, it's going to be positive 8.
It's going to
7
be-
minus 1. Yeah, it's going to be positive and the other one
He's
negative.
Well, that's why the overflow flag is a 1 because the sign of the result makes no sense.
Oh, okay.
Okay, I'm just looking at the bit pattern and say, okay, if I want to interpret, okay, this is what I'm doing. I just look at the bit pattern, and I say, if I want to interpret this bit pattern here using the signed interpretation, what does it mean? What is the value represented by this bit pattern? It is representing the value negative 8. If I want to use the unsigned interpretation, what is it representing? It's representing the value 8. So that's why the result does not seem to make any sense because it does not make sense. That's how the overflow flag itself, is a 1. Is that okay so far? Okay. Okay. So using the signed interpretation and using the same notation that we have used so far, this is our y, this is our x. Okay, and this is our result, which is which is not important here. Which one is the larger one? Y is larger than x, and this time the carry flag is a 1. If you look at the unsigned interpretation, what do we have? Y is less than x, and the carry flag is a 1. So we have 3 cases worked out at this point. This is our first case. Okay, just look at this part here. Y is less than x in the unsigned interpretation, the carry flag is a 1. Y is greater than x in the unsigned interpretation, the carry flag is a 0. Y is less than x, and the carry flag is a 1. So all three cases are consistent. Whenever y is less than x, the carry flag or the borrow flag is a 1. Okay? But we don't have such luck with the sign interpretation, because all you have to do is to look at, let's see here, look at these two interpretations. In using the sign interpretation, the carry flag is a 1 when y is greater than x. Using the sign interpretation, they're consistent.
But opposite?
Hmm?
They're consistent but opposite from the unsigned.
Yeah, but it's still indicating y is larger than x.
Because y is larger than x.
Okay, I just don't have one normal subtraction that is not.
Don't trust tag.
Okay, that's easy. I can generate one just like that. Okay, let's look at this one here. The result is, well, that's easy, right? Okay, so in this case, you tell me what are the flags. Start with the carry flag.
0.
Okay.
0. 0.
Okay. And now this time, whether it's a sign or not. This one is so easy. I'm not going to interpret the bit patterns because in either case they're the same. In the sign interpretation, y is how does it compare to x?
Y is greater than x.
X, and yet the carry flag is a 0. And that's all I have to do, because all I want to do is to show you the carry flag by itself is not enough to tell you which number is larger.
Well, let's look at the unsigned.
Hmm?
Let's look at the unsigned.
And if you look at the unsigned, it makes sense, okay? Because if you look at the unsigned, y is still greater than x, and the carry flag is a 0. Oh, but we haven't checked one special case. What if x and y are exactly the same? Would the carry flag still work in that case? No, we will still be consistent. Okay, let's take a look. I mean, this one is kind
No,
of
in that case,
trivial.
the 0 flag will be true.
It's still
We'll check that
consistent.
instead.
It is still consistent. Okay. And the overall borrow is a 0. Okay. So we have C equals 0, C equals 1, S equals 0, and O equals 0 in this case. And we have in sign interpretation, y is greater than y equals x. And using the unsigned interpretation, y equals x2. Now, but the question is, when the carry flag is a 1, does it tell me something? Is there any consistency at this point? When the carry flag is a 1, y is less than x.
Only for unsigned.
When the carry flag is 1, y is less than x. What happens when C is 0, when the carry flag is cleared? When the carry flag is cleared, y is greater than x, but I can also generalize and say y is greater than or equal to x, which makes the last case also consistent, because when the carry flag is 0, y equals to x. So that means, okay, out of this whole discussion, that's one thing that we know for sure. C equals 0, if and only if...
C equals 1.
That's a matter, I can change the comparison, right? Right?
For unsigned.
Exactly. But only for unsigned interpretation.
So if we're doing unsigned, all we need is that C and the Z flag.
Then you have all the results.
And we've got less than, greater than or equal to. Wait.
Yeah, if you take the combination, you know whether it's greater than or not.
Yeah,
Right?
we've got less than, greater than, and equal to. We've got everything we need to build any other
Yes,
complex
exactly.
comparison. We're done. We can go home.
We can go home unless we want to talk about the signed interpretation. Okay, but is that okay so far? Does everybody understand this last sentence here, the conclusion of what we have talked about so far? The carry flag is useful in a comparison, but only if you are dealing with unsigned numbers, or if you choose to interpret the bit patterns as unsigned numbers. Now this is big, okay? This is, even though it's a lot of tedious, details, bitwise operations or whatnot. In the big picture, this is very important because what do you deal with? How do you deal with signed versus unsigned in C? You say signed int to declare a variable that is supposed to be interpreted signed, and you say unsigned int to declare a variable that is supposed to be interpreted unsigned. Once you have the type associated with the variables, when you do a compare, x is less than y, guess what? The compiler takes care of that for you, okay? But not in assembly language programming. When you say x colon dot int whatever, y colon dot int something, you are only allocating 4 bytes each. The labels correspond to the first byte of each allocation, and you specify the bit pattern that goes into the 4 bytes. When you say compare, okay, you cannot use two direct operands, but let's say you can. When you say CMPL y comma x, okay, the comparison will happen. It will do the subtraction just fine. But then how do you know which number is larger? Which flag do you pay attention to? That determines which number is larger.
L flag.
Okay, so in this case, the L flag works for signed interpretation. The C flag works for unsigned interpretation. And that's why there's a big difference in terms of how we treat signed versus unsigned. In C, C++, Java, and just about any high-level programming language, once you declare this variable is signed versus unsigned, the rest is taken care of by the compiler. You can just say compare, and it's going to work. Okay? In assembly language programming, it is the choice of the instructions that will determine how you look at the numbers. Are you looking at the numbers as signed, or are you looking at the numbers as unsigned? Because you can choose whether the next instruction, to pay attention to the C flag, the Z flag, the S flag, the O flag, or the composite L flag that we have not talked about so far. Is that okay? Because this is the overall picture. This is taking a step back, not looking at the details, but to point out the main differences between C programming versus assembly language programming. Yes?
Since we're wrapping up for the day, I can't help but notice that you haven't mentioned how to deal with decimals yet.
Decimals?
Yeah.
As in point,
yeah,
2.56?
Yeah.
Something like that?
Other floating point numbers.
Oh, we're not going to deal with that. At least not for now.
Okay.
Because that would just throw another big wrench into the whole thing. We're not ready for that yet. So please review what we have talked about so far before next Tuesday. And then on next Tuesday, we will talk about how to interpret the flags for signed comparisons. So read ahead of me, otherwise it will be confusing like heck.
We're going to practice exam.
Oh,
Anything, or are we not having exam next